here you got m1 plus little m times the new velocity is basically how you solve it. So they're asking for the final velocity. That's your final velocity here. I mean, you can call it anything you want. I'd rather call it VF. They call it V prime in the book. But just solve now for VF. So VF is this quantity divided by that sum there. So it's mv0 divided by m plus little m. And there you go. That's your solution in a completely inelastic situation. Now in elastic, there's conservation of energy. So you're going to need to combine those formulas. Now, conservation of momentum, in this case, you're going to have, like we said, m v0 is equal to m v prime plus little m v prime. Okay? So those are two different velocities there, they're just small. And basically, that's basically what's happening there. You have the momentum of the first one at its velocity, and they're each going to have their own new velocities at the end. So you just want to solve for each of those separately, and what that's going to do is give you the final velocity in the system. Okay. One key or two key things that you want to know is in conservation of energy. You also know that 1/2 m v0 squared is equal to 1/2 mv prime squared plus 1/2 little m v prime squared. Sorry if my handwriting is not good, and hopefully it's showing up on the camera there. But basically, what this is just showing you the conservation of energy laws. There's also a way that you can derive some other formulas too from your initial equations, but I'm just going to kind of write those down now. There's also v0 is equal to little v minus big V, and little v prime is equal to v0 plus v. Okay, so you'll kind of want to use those two along the way. If you plug those in to this equation up here, you're going to get the right solutions. These are kind of stuff that you probably want to commit to memory anyway, but if you plug in, do the algebra, you're going to find that that little v prime prime is equal to 2mv0 over m plus m, little m. Okay, and then the other velocity, big V prime, equal to v0 times m minus m all over m plus m. And it's just a matter of knowing these formulas here being derived. It basically is like, to get to here, you basically use v1 minus v2 is equal to v2 final minus v1 final. And I just simplified into these little ones here because you don't need all those variables. So okay, but basically those are going to be your final velocities. So just work the algebra. If I had more time on this videotape, I'd work through the problem a little bit more for you. But hopefully you'll be able to plug through that algebra and see. But the key things to remember about this is conservation of momentum, conservation of energy. In elastic collision, remember elastic is going to give you energy, conservation of energy. Inelastic, there's no energy. There's no conservation of energy you need to use. So just remember that for your formulas, and that should help you down the line. Okay, next question. Describe the motion of the block spring assembly when the block is displaced 4 inches from the equilibrium position. Okay, so basically they're just going to give you a block system here. They kind of draw it like this. Give you a little spring. Tell you that this is K. And that this is M. Okay, so main things here that you need to know is that the force of the spring, and these are just formulas that you need to commit to memory. The force of the spring is equal to negative K times X. Okay? And here you also need to know one of Newton's laws there, F is equal to ma. Well, in this case, ma you can basically do m times, well, the second derivative of position. The first derivative of position is velocity. Second derivative of position is acceleration. Okay, so you can convert acceleration into the second derivative of position with respect to time. Okay, so basically in this situation, m times second derivative of position over dt is equal to negative k x. Alright, same over there. And then basically you just solve. You just solve. Okay, so here you have d2x plus k over mx is equal to 0. So just a little bit of basic algebra there. And here, you kind of need to use, with these spring systems, you kind of need to use a little bit of some of your differential equation knowledge. You're basically going to use the form of a cosine blah plus b cosine blah to get your differential system in line. So basically here, you let just omega, you can call it whatever you want, but let omega squared equal to k over m. Okay, because this is a differential equation. Acceleration is the second derivative of position. Okay, and you just need to know this so that you can get this all worked out. So basically, you're just going to do basic differential equation solving here so that you can get everything taken care of. So you also know some initial conditions here. At time is equal to 0, t equals 0, x is equal to 4. They tell you that in the beginning. They tell you that the position is 4 inches from the equilibrium position. Okay, and they also say that the velocity, the derivative of position is velocity, right? Well, that initial velocity is 0. So at time 0, you want to use your fun differential system. There's only two types of differential systems that you can use. The one involves your natural exponent, and the other one involves cosine and sine. So, I mean, you basically just need to know it. So, without going into too much detail on it, position, okay, I think I have enough room here, hopefully, guys. Position 4 is equal to a cosine omega, right? Cosine omega, that's not squared, that's just 2. Cosine omega 0 plus b sine omega 0, which implies a is equal to 4, okay? Because cosine of 0 is 0, okay? So a is equal to 4 in that case, and cosine of 0 is 1, all right? And at the 0, so that's the 4 scenario, at the 0 scenario where velocity is 0, that is 0 is equal to 4 sine omega plus b sine omega, which implies b is equal to 0. Okay. Probably running a little bit off the board here, sorry about that. Let me double check here. Let's check. Okay.